So for 361, what I wanted to do was to give you a video covering the presentation on the VGA design, and I'll finish up with the first assignment. We'll talk about it in class, but I need to make sure that the information is out and everybody is up to date with what we're doing. So just an overview of where we're at. The first third of the class, we went over what I would consider the more advanced digital design technique, synchronization, synchronous design, just how to do digital design, how to come up with certain solutions when you're faced with problems, how to keep track of elapsed physical time when you're dealing with such fast numbers as, let's say, 10 nanosecond clocks. The second third of the class is dealing with verification, but the verification aspect will be done in the context of VGA. And this portion is presented in Pongchu's book. I would encourage you to read it and study what Pongchu has to say. My presentation utilizes information from Pongchu, and it gets us in. So we'll use the VGA, but we'll use it as the backdrop for verification. So to get going, the first thing we need to do is understand and develop a working understanding of VGA so that we can create our first project. So VGA stands for Video Graphics Array. It's a video display standard introduced in the late 1980s. I might have mentioned in class, early on, the computers we had were all text-based, meaning that all you could see were the letters, the numbers, and the punctuation symbols. No graphics, other than some very rudimentary lines that you could create. So with VGA, changed the approach to how the information was displayed on a computer terminal. We'll be using, of course, our Nexus 4 board. It supports VGA. Our design will use a 640 by 480 resolution. Clearly, by looking at the displays of your own computers these days, you can see that they've advanced quite beyond this. But we'll get our feet wet with a 640 by 480. And we'll design the interface, create the test fixtures, and run it on our board. So the basic concept came from a cathode ray tube, a CRT, where they were sending out the information, basically electrons, to hit a phosphorus coated screen, and they would use fields, electric fields, to change the flight of the electrons to determine what patterns would be shaped when it hit the display. In essence, it looked like this, where you would have your display, you'd have your beam, the beam's flight would be adjusted by the different coils, and then you would display the images on the CRT. This, of course, is not where we're at. We're in a digital world. But what we do still maintain is the need to maintain a horizontal sync and a vertical sync. And what this does, this allows the sender and the receiver to always know exactly what pixel is being displayed on the display at any given time. The display is presented in this manner. It's a scanned pattern, the solid lines showing the path that the display is updated. If you recall, we have 640 that's across, 480 that's down. They reference the upper left-hand corner as 00, so it goes 0 to 639 and 0 to 479. The display is updated as it moves from left to right. Once it reaches the right side, they have a retrace, they call the horizontal retrace. It's dotted because at that point in time, nothing is being displayed on the terminal. Once they return to the first column, they continue updating the display. And what happens is, as this is done over and over again very quickly, it gives the user the impression that they're seeing an image from top to bottom, left to right. And the whole goal is to keep the frequency of the display moving fast enough that the user doesn't have any sensation of any kind of flickering. The color was driven by the RGB. And for us, we're going to have 4 bits of red, 4 bits of green, 4 bits of blue. 2 to the 12th is 4096. So we're going to have 4096 different colors that we can display. The connector is shown here, and basically when you say you have a VGA cable, we don't have to think about it because the cable is created according to the following pinout. What is of interest is what signals are required to convey the VGA signal from the computer to the terminal. In this case, we're going to have 4 red lines, 4 green lines, 4 blue lines, and then our aforementioned syncs, the horizontal and vertical sync. That is it as far as the signals that we send to the display. What we're going to be doing eventually is having a complete system where we'll have a VGA controller, where we'll be generating a pattern on the display and controlling it. Initially, what we're going to do, we're just going to generate the VGA sync that will create the horizontal and vertical sync, and we'll make sure that the terminal is able to recognize our sync, and we know then we're ready to begin communication. So the video synchronization, as mentioned, there's the horizontal sync and the vertical sync. So the horizontal sync is the required time to traverse a row. The vertical sync is the time required to traverse the entire screen. So we will use a 25 megahertz pixel rate, meaning that 25 million pixels will be processed in 1 second. Then the CRT monitor will include a black border around it with a visible portion in between. The top left will be 00, the bottom right, as I mentioned, will be 639, 479. The display is created, as we saw before, with the horizontal scan, the horizontal refresh, comes all the way down, then jumps back up. There is a timing relationship. The horizontal counter will run from 0 to 799. The display will utilize 640 of that count. There will be a 48 count that's used on the left-hand side that we won't be displaying any information. There will be, I believe, a 48 count on the right side as well that we won't display any information. That's referred to as the back porch. This is the right porch, that's the front porch. The left border is called the back porch. We won't use that terminology. But what we will utilize is the fact that we're going to have 48 pixels not displayed here, 48 pixels here, and we'll have 0 to 639 coming across. So this shows, and we also have a time it takes to retrace. So for our horizontal scan, these are the numbers. We have from the beginning, we'll display the 640, we'll have our porch, the retrace, the back porch, and away we go again. Notice that the video on signal is active whenever we are sending data to the display. When we are passing through the porch or doing the retrace, we do not have our horizontal video signal on. So for the vertical line, it's similar in that there's a vertical video on that will be off whenever we're not displaying. The vertical sync will take us through our top border, then through the 480 rows, and then again another border at the bottom, and our retraced time. So for the horizontal definitions, the display is the region where the pixels are being displayed. 640 pixels. The retrace is where the beam is returning back to the left-hand side. The right porch is the area on the right. The left porch is the area on the left. And I think that front porch number is wrong where I say 16 pixels. We just saw that it should be 48 pixels. Horizontal. 48 left border. Oh, 16 on the right border, so I was wrong. So left border 48, 16 on the right border, so that's correct. For the vertical definition, we see that we have the horizontal lines being displayed, 480 lines. The retrace is the time it takes to get back to 0, 0, traversing the entire screen. So again, we're going to have this border on the top, 10 lines, border on the bottom, then the displayable region in between. The H-sync signal may be obtained from a mod 800 counter and a decoding circuit. The counts are used as the milestones for the display. The V-sync signal may be obtained from a mod 525 counter and also a decoding circuit. This count is used also as the milestones for the display. This shows the math of what we're accomplishing. So we mentioned that the pixel rate is 25 megahertz. How we come up with that is that we have the number of pixels in a horizontal scan. So for the 640 by 480, there's 800 pixels per line. Then with the lines, we have 525 lines per screen. Then S is the number of screens per second, and we said we're going to update the screens at 60 hertz, or 60 screens per second. When we do the math of the P times the L times the S, we end up with 25 million pixels per second. So the rate for other resolutions and refresh rates can grow, but this is what we're going to use for our display. So here's some calculations just to kind of give us our, once we do the math with our clock frequency, we're going to end up with a screen refresh rate a little bit over 59 hertz. Our pixel frequency will be exactly 25 megahertz, which we'll be able to derive exactly from our 100 megahertz clock. If you consider a 100 megahertz clock divided by 4, will give us our 25 megahertz. And then you do the math, you can see the actual time that will be consumed when we're doing the display through the different portions of the vertical and horizontal display. So the requirements, and for our verification approach, we're going to be designing according to requirements, and then we'll discuss it when we write the actual verification. It will be your job to demonstrate that your design meets all of these 12 requirements. So these are the synchronization requirements, the requirements. This is what you need to do in order to create a design that will perform correctly. And let's just walk through them quickly. So reset is high active and asynchronous. It brings the machine to a known state. The VGA sync logic is updated at 25 megahertz. The horizontal scan count should be updated at the 25 megahertz rate. The horizontal scan count shall range from 0 to 799. The horizontal scan sync signal shall be low active and shall be active from horizontal scan count 656 through 751. The horizontal video on signal should be high active. It should be active from the horizontal scan count 0 through 639. The vertical scan count shall be updated at the completion of the horizontal scan. The vertical scan count shall range from 0 to 524. The vertical sync signal shall be low active and shall be active from vertical scan count 490 through 491. The vertical video on signal shall be high active and shall be active from vertical scan count 0 through 39. The overall video on signal shall be high active and shall be active when the horizontal video on and the vertical video on are active at the same time. For us, the RGB signal shall be driven while the video is on. Video on is active, and when the video on signal is inactive, the RGB signal should be held at 0, which will display the black character, so we won't see anything. So this is basically a quick overview of what VGA is and in essence how the computer is able to synchronize with the display. As we progress through this 5-week period, we'll get more into it and see exactly how we can display objects. So after we have the presentation of that, now let's look at our first assignment. So our first assignment is going to be based on the VGA Intro lecture we just went over. You can always use Peng Chu as a reference. He's an excellent reference with these topics. I think it's an excellent idea to understand how Peng Chu has done his work. Of course, my recommendation is always that you do your own work once you understand what it is you're supposed to do. The assignment is to code the design for the VGA synchronization block. Our next assignment in a couple weeks will be to verify the design and implement it, and then we'll put it on our board. So the approach now is that we're just going to do the portion in the green area. We will not be generating pixel signals, but the output of our block, we will have the RGB, but the RGB is going to be driven by the switches, so that while the sync is running, we can flip the switches and we'll see the entire display switch to the color chosen by our 12 switches. Here's a recap of the requirements we just looked at. And before writing any Verilog, you should create a document that will serve as your guide. You should come up with a plan. Then create this circuit to create the VGA syncs, and then have the RGB signal sourced from the 12 switches so that as your sync is running, you can flip the switches and see the color change on the display. The project's due on October 10th, like I said, a couple weeks. That'll get us going, and then we'll transition from the creation of the design to the verification of the design. Okay, so good luck. Hope everything is going well.